Okay, so in this video, what I'd like to do is approximate the area underneath this curve, and I would only like to focus on the region from one all the way to 5. So I only want to focus on this region right here. And again, I don't want to find the exact area. I just kind of want to approximate it, and we're going to do this by using a set of rectangles to do it. And so what I'm going to do here is just begin by sketching a rectangle right here, and I've just decided to use the leftmost point right here to the curve. So you'll see what I mean as soon as I sketch my rectangle. Notice that I'm not going up, I'm sketching a straight rectangle, but I'm using this corner to kind of guide myself along this curve. So again, I have my first rectangle right here. There it is. And then what I'm going to do is sketch another one just like that. But again, I'm going to use the leftmost side to kind of guide me through. And so there's my second rectangle. Let me just kind of sketch it a little bit there too. Okay, and then let me change color and let me do my third. Let's see my third rectangle here. Okay, so there. Oops, there's my third rectangle. And finally we have our last rectangle, and I will do this in blue, a different shade of blue. Let's see. So there's my fourth rectangle. So yeah, I've drawn a total of 4 rectangles here to kind of give me an estimation or some type of approximation to the area underneath this curve. Okay, so what I would like to do is find the area of each rectangle. And the really cool thing about doing this is that you know already a formula for the area of a rectangle. It's just the length times the width. Well, the question is, well, how do you figure out what the width is? So we call the width delta x. And I just want you to assume that the width of this rectangle is equal to the width of this rectangle, and the width of this rectangle, and the width of this one. In other words, all the rectangles are equally spaced out, and they have an equal width all the way through. So that would mean that this guy here is also delta x. And if I finish off this width of this pink or magenta rectangle here is also delta x. And finally, our fourth rectangle here is delta x. Now the question is, well, what is the height? What would be the height here? Well, if you look at how I drew each rectangle, notice the left point touches the curve. Well, what is that x value here? Well, it's 1, and if you think about plugging in 1 into the function, you get out the height. So this height just ends up being y of 1, since our function here is in terms of y, so it'll just be y of 1. Whatever that is, you can plug it in and figure it out, and we'll do that later. Furthermore, if I move on to this one, what would be the height of this light blue rectangle here? Well, it looks like you would need to figure out what this number is. And looking at the picture, you could probably easily guess that this is going to be a 2, this would be a 3, this would be a 4, and this would be a 5. But what if the numbers weren't as nice as this? How do you figure it out? Well, it's pretty straightforward. To figure out the width of a rectangle, to figure out what delta x is equal to, turns out that, and remember, keep in mind delta x is the width. Well, delta x is equal to the last, wherever you're ending, so we're ending here at 5. Take away where we're starting from, so 5 minus 1. And we're going to divide that by how many rectangles we have. Well, we have a total of 4 rectangles, or we can think about it as 4 intervals. And if you do the math here, 5 minus 1 is 5. I'm sorry, 5 minus 1 is 4, and 4 divided by 4 is just 1. So that means each width is 1. So 1 plus 1 is 2. 2 plus another width of 1 would be 3 here. 3 plus another width of 1 would be 4. And finally, we add the other 1 and we get 5. So it turns out then that this height here would be y of 2, and I'm just going to finish this off. That means this one here would be y of 3, and our last rectangle here would be y of 4. And you can think about it like this, that I'm talking about this point right here, that these dotted lines are touching on the curve. And so we're now ready to find the areas because we now know what the width is and we now know what what the height is of each rectangle. So let's go ahead and do that. Let's see here. I'm going to shade in this one here. And I'm going to call this guy, I'm going to call him R1. So the area of R1 is simply going to be y of 1. It's going to be the length times the width, which is delta x. That is the area of R1. If we move to rectangle number 2, I'll call this one R2. The area of R2 would be the length. Remember, the length is given by the height, so it's going to be y2 times the width, which we said was delta x. And if we keep moving along, we have this third rectangle. I will call that R3, and again it would be given by y of, let's see, y of 3 times delta x. And then finally we have the last one, which I'll call R4. So I'll call that R4. So the area of R4 is going to be y of 4 delta times delta x. Well, you found essentially the area of each of these 4 rectangles, but what I want to do is approximate the area underneath the curve. Well, if you think about it, if I had this rectangle, if I had the area plus the first rectangle, so this one here, plus this one, which I forgot to label R3, plus the fourth one, then I would get essentially a pretty good approximation underneath this curve. So what I can do now is just add up all the areas, right? So I could just say y1 of delta x times delta x, plus y2 times delta x plus y3 times delta x plus y4 times delta x would give me some type of approximation. So this would give me some type of approximation of the area under the curve. That's pretty good. So we have a formula now that can tell us what a good approximation would be under the curve. But I want you to think about what we have here. It looks like I am adding up a bunch of terms. And if you think back to the previous video that we just saw, this looks like a sum of 4 terms. So I could actually, this is actually equal to, if you think about it, we have the sum from of some function. It looks like y of x times delta x, right? It's y of 1, y of 2, y of 3, and each of those is being multiplied by this delta x. So it looks like our function here would be y of something times delta x, and it looks like x is going from 1 all the way to 4. And so what we have here is a sum of different terms. Now we can go ahead and evaluate this and finish off this problem. For instance, we know delta x already. We know what delta x is equal to. Delta x is equal to 1. So if I do this really quick here, y of 1, if you think about plugging in 1 here, 1 squared plus 2, that's going to be 3 times 1. Let me actually keep this color coded so we don't get lost here. And then we have plus, let's see here, y of 2 means I plug in 2 here, so 2 squared plus 2 squared is 4, so that's going to give me, let's say, 6 times 1. Then I'm going to have this plus here, and y3, let's see, if I plug in a 3, I'll get 11 times delta x. And then finally I will have this plus, this plus y4, which means I got to plug in 4 here. So 4 squared, 16 plus 2 more, that's going to give me 18 times 1. And I should change this, I should change this here to a times 1 since we are plugging in delta x, and delta x is 1. And so now you can just evaluate this, and I'll leave this to you to do because you can just add up these numbers here, and whatever number you get would give you an approximation of the area underneath the curve.